This shape begins with one very small equation. But every edge seems to contain another universe. When you zoom in, the boundary keeps answering. What if a formula could remember its whole past? Endless detail waits. Here is the path we will follow today. First, we meet the strange shape on screen. Then we watch the two-letter equation do work. Then IBM computer pictures reveal Mandelbrot roughness. After that, copies appear inside copies at smaller scales. Finally, nature shows why this picture feels familiar. Look closely at the black island near the center. Its edge is not a normal outline at all. Every small turn contains bays, spikes, and threads. Each spike opens into smaller spikes and smaller bays. So far, the picture looks almost impossible to draw. Yet it comes from one tiny repeated test. The test begins with z equals z squared plus c. The letters are small, but the loop is huge. Start with z at 0, then choose c. Now run the same rule again and again. Watch whether the value stays near the center. This repeated rule is what we call iteration. Iteration. Some points stay near the center for a long time. Other points run far away very quickly instead. If a point escapes, we color it outside. If it stays trapped, we color it black. The Mandelbrot set is the trapped region in black. The picture lives on the complex plane itself. That plane is a flat map for special numbers. One direction shows ordinary value on the grid. The other direction shows imaginary value on the grid. Each pixel becomes one possible choice for C. The computer tests those choices one by one. Now jump to IBM in the year 1980. Benoit Mandelbrot was studying rough shapes there at work. He cared about coastlines, prices, and noisy signals. Those things looked messy, but not completely meaningless. They carried patterns that changed with viewing scale. He needed computer pictures to see them clearly. Early computer graphics made the set visible at last. The first images were rough and heavily pixelated. But those pictures showed something nobody expected to see. A simple formula drew a strange black continent. Around it, colors formed burning halos and thin filaments. Boundary steals focus. Here is the trick in the history. The equation alone was not the whole discovery. The screen made hidden behavior visible for the first time. Mandelbrot turned calculation into a visual landscape. That landscape gave roughness a new visual language. Fractal became the name for that new language. Now the rule changes scale under the camera. Zoom into the edge, not the center region. You may find a tiny copy waiting there. It looks like the whole island again in miniature. The copy is warped, crowded, and glowing with color. Still, the family resemblance is clear to your eye. This is self-similarity in action across changing scale. Self-similarity is repeated structure across scale. It does not have to be perfectly exact. The copies can twist, stretch, and crowd together. But your eye still recognizes the same rule. The same equation keeps drawing visual echoes again. Self-similarity. Every zoom asks the same question again below. Does this new point stay, or does it escape? The answer paints another layer of colored detail. Then the camera moves closer and asks again. No artist is adding ornaments here by hand. The ornament comes from repeated testing of each point. This is why fractals can feel so natural. A coastline also changes when you zoom in. From far away, it looks almost smooth enough. Up close, it breaks into smaller rough bends. The way roughness repeats across scale really matters. Mandelbrot used that idea far beyond visual art. Clouds are not perfect copies of Mandelbrot sets. Branches do not run z squared plus c. But they share a deeper habit with fractals. Small local rules can build rough edges over time. Rough edges keep detail at many viewing scales. Nature often grows through repeated local choices nearby. So far, one rule has done the work. It tests points, draws a boundary, and repeats. It creates islands inside smaller islands along the edge. It gives roughness a shape we can measure. That is the power of fractal thinking here. It makes messy edges feel structured and readable. Return to the first black shape again now. It was never only a beautiful mathematical picture. It was a map of long behavior over time. Each pixel carried a little future inside the loop. Some futures stayed near home for the loop. Some escaped into distance very quickly instead of staying. Edge remembers both. The opening promise was strange from the start. One equation could contain another universe inside its edge. Now that universe has a clear visual method. Repeat the rule, test escape, color the answer. Then move closer and ask the question again. The formula is tiny, but the boundary is not. Between them lies a patient loop of tests. It does not draw by adding extra rules. It draws by asking one question forever instead. Edge infinity waits.